Good morning. Welcome to RMS618 Module 2, Presentation on PowerPoint. Our topic today will be multiple regression. Its purpose is to predict the outcome based on several predictor variables. Now in this particular case, in multiple regression, we have some requirements. Our dependent variable is always continuous. The independent variables, the predictor variables, can be either continuous variables or dichotomous variables. And we would prefer a large number of observations. We're going to look at an example here. We're going to examine the predictors of blood pressure. Now here we see the simple linear regression case. Here we see the multiple regression case. So we see that the only difference between this and this is that in this we have multiple predictors. So in this case we're going to have multiple betas. It's always important that we check assumptions before running any simple linear or multiple regression equation. If the assumptions are met, there's a high likelihood that we're going to have a pretty accurate prediction. If some of the assumptions are violated, the coefficients will be most likely less than accurate. Homoscedasticity, we know that that's considered homogeneity of variance. The variability of the residuals must be the same or similar for all values of the predictor variables. Normality, we know that the residuals should be distributed normally. We can look at that through histogram. Collinearity, if there's too high of a relationship between the predictor variables, it decreases our ability, again, to accurately predict y from x. We have some measures. Tolerance should be greater than 0.20. Variance inflation factor less than 4. Checking the assumption for homoscedasticity, we'll look at a scatter plot. X and y in terms of the residuals. For normality, we can look at a histogram or what we call a normal PP plot. And for collinearity, we're going to check tolerance and variance inflation factor. Here we have our SPSS screen. We're going to bring standardized residual and Z predicted into the boxes. It's going to give us a histogram and that normal probability plot. And we click on estimates and model fit, hit continue, and we get the picture. We get the picture. Is there homoscedasticity? Okay, the answer is yes. The answer is yes. Okay, this is a plot characteristic of a situation where we have, homogeneity of variance, homoscedasticity. If the data points were to converge, it would suggest heteroscedasticity. So we have satisfied the assumption of homoscedasticity in this particular case. Does this show a normal distribution? Absolutely, absolutely. So we have, we have normality. Is there a normal distribution? The answer is yes. If these data points conform or they adhere to this particular line, we can conclude that we have a normal distribution. And again, this is the PP plot. We can use either the histogram or the PP plot or both. Collinearity, and these are collinearity diagnostics. As we see, both tolerance and variance inflation factors are within the acceptable limits. So we are good on collinearity. We are good on collinearity. We are satisfying the necessary assumptions. Does this graph indicate that the assumption of homoscedasticity has been met? Well, look at this graph. What is this? This is a scatter plot. What does this show us? Well, it shows us a linear relationship. This actually shows us a linear relationship between x and y. So it actually shows us that the assumption of linearity has been met. Okay, so we have fairly strong positive correlation between X and Y, whatever that may be. Checking outliers. This shows us how to do it. Click on standardized residuals. We have our data set. Okay. If our Z residuals are greater than 2.6 or less than negative 2.6, we are, not in acceptable range. Why? Because we know that 99% confidence interval, these are essentially the cutoff points. So we see in this particular column that we are within the acceptable limits. We are within the acceptable limits. What this is saying is that for all practical purposes, there aren't really any glaring outliers in this particular data set. So we're good on outliers. Dummy coding, when to use. Okay. When we are transforming categorical variables into some dichotomous variable, we want to use dummy coding. So again, we're using categorical variables. Okay, and we're going to reduce some categorical variable that is coded with 2 or more, 3 or more codes down into something that is dichotomous. So we see an example, the private school variable can be reduced to a new variable that is dichotomous, okay, 0s and 1s. The charter school variable can be reduced to a dummy-coded variable that is coded either 0 or 1. So this is just a process of reducing categorical variables into a little bit more specific dummy-coded variables with 0s and 1s. Creating dummy codes. Okay, we bring the general variable school over and do our work here with the output variable. And then we'll continue. Old values, new values. Okay? So we fill in what the old value is, and then we put new values, and then we continue. And we have our data set, and so now we have our new we have our dummy-coded private school variable, 0s and 1s, dummy-coded charter school variable, 0s and 1s. This is a situation where when we get to logistic regression and we want to predict whether a set of independent variables predict attendance at private schools, we can actually use that variable. So it's just converting one categorical variable to something a little bit more specific. Selection methods. In this particular course in advanced statistics, we're using 3 selection methods: simultaneous, stepwise, and hierarchical. And we'll start with the just the basic the first method. We'll call it entry. Okay, so that simultaneous method is also called entry or enter. We see the SPSS screen, we bring the dependent variable in, and then the 3 independent variables. We're trying to predict reading ability from Word, Private, and Charter. Okay? We will continue. Here is our model. The model accounts for 51.8% of the variance. This number is obtained right here from adjusted R squared. Okay? So 51% of the variance in the dependent variable can be explained by the independent variable. So this is a moderately predictive model. This model is significant. Why? Because this p-value is very, very, very small. So p is definitely less than alpha. The model is statistically significant. And in terms of notation, this is the proper notation. Okay, 5 and 279 degrees of freedom. Our F value, P is less than alpha. P is reported, and it can be reported that way too. So we have a significant model. And now we have our coefficients, and we see we have B and beta, non-standardized, standardized. So again, these are to whatever variable scale we are. These have been reduced to a scale between 0 and 1 or 0 and -1. We put an equation together. Reading equals 0.085. That's the y-intercept, plus 0.673 listening, plus 0.240 visual, minus 0.037 word, minus 0.150 private, minus 0.10 charter. So as you see, they just took the independent variables, listed them from highest to lowest in terms of their strength, in terms of their ability to predict the dependent variable, reading. Let's go back. Yeah, here we go. Which variables are statistically significant? Well, let's look. Listening, visual. Word is non-significant. Private is significant. And charter is significant. Okay. Stepwise regression. Okay. So instead of entering all the IVs at once, in stepwise regression, the computer is going to determine which of the independent variables is the most predictive, and then enter each one at a time, and so that they are ultimately combined to see what kind of model we end up with. So again, you see the method is stepwise. So all the stepwise procedure is doing is entering the variables one at a time to see which ones or combinations of variables contribute most to prediction of the dependent variable. We have our screen. We click on estimates, model fit, R-squared change, and we continue. Here we have our output. Now this is really interesting. Look at what's happening here. Okay, with just listening as a predictor, here's the overall R. With listening and visual, overall R is increased a little bit. With listening, visual, and private, it's increased even more. And when the 4 independent variables are combined, it's increased even more. We see significance in all our cases. So we see actually the strongest model is the combination of listening, visual, private, and charter. Model 1. So we're addressing model 1 here. Listening alone accounts for about 44% of the variance, and that's right here. In model 3, listening, visual, private, and charter accounts for 51.8% of the variance. And that actually should be model 4. Okay. All in all, I think you guys see what's going on. Okay, let's continue. The ANOVA. And again, we have the ANOVAs for all 4 situations. And again, these ANOVAs are all significant, as indicated by these very, very, very small p-values. Okay? So again, we have a significant model, actually 4 significant models in our stepwise regression procedure. Coefficients. So again, we have equations for each of these situations. So we see that model 1, 2, 3, and 4. And we can put these equations together, accordingly. Okay. Hierarchical regression. This is a little bit similar to stepwise, but a bit different. Variables are introduced in steps. The researcher actually makes the decision as to what variables to introduce first or second or third based on theory and historical research based on the literature. Okay, so the researcher is actually responsible for entering, potential significant independent variables. In this case, to predict reading. Okay, so enter is used because the researcher is going to physically introduce variables as he sees fit. We see our screen. We bring the variables over, and we have the models. Okay, we have the models. Now you see a lot of similarity with what's going on here. Okay, and again we have a couple of significant models. Okay, we have a couple of significant models. Model 2 appears to be more predictive than Model 1. So the independent variables, charter, private word, visual, and listening combined together appear to be more, a bit more predictive than the model that just contains charter and private. Now again, these variables were entered, by the researcher. Okay, hierarchical regression. 40.3% of the variance explained after the influence of school, listening, visual, and word is removed, and this number is right here. Okay. So we have various ways of conducting multiple regression. Here we have the ANOVA indicating significance of the models. Okay, and again we know that because these two p-values are substantially less than alpha. We know if p is less than alpha, we have significance. Here we have our coefficients. Again, we can put the equations together, and they have done that for us here. Reading equals 0.085, and so they've used this model. This is the y-intercept, minus 0.15, minus 0.10, plus 0.673 listening, see that? Plus 0.224 visual, minus 0.037 word. So to summarize, when to use multiple regression. Okay. Multiple regression is used when we have multiple independent variables predicting one dependent variable. We like to have as many subjects as we can. We can create dummy codes if needed. We always check assumptions. Select the appropriate regression method. There's a lot of just forced entry. There's a lot of stepwise out there, and there's a lot of hierarchical regression. And we run the analysis, according to the instructions. Let's try SPSS exercise number 1. Perform multiple regression on M1conference.save to determine whether age and height are predictors of quadriceps strength. Describe and interpret the results. And then it asks us, these questions. These are pretty basic questions. R squared, adjusted R squared, p-values. What's the equation based on the coefficients, and which one of those coefficients is statistically significant? Here we go. The model is, I would say, moderately predictive in terms of the overall model, and it accounts for about 22.2% of the variance. And again, that number is obtained from adjusted R squared. Here we have the ANOVA. We have a significant model. P is actually 0.003, substantially less than 0.05. We have a significant model. We have rejected a null. And again, you see the notation. This is the proper notation. 2 and 38 degrees of freedom. See, 2 and 38 degrees of freedom. Here's our F value. And they've, in this case, reported an exact p-value. So they could report this as p is less than 0.05. They chose to report the exact p-value. Okay. We have our coefficients. We see significance here and here. We see significance. Okay. P is less than 0.05. They put this equation together, okay? Y, and it could be y prime, equals negative 465.626. This is our y-intercept, minus 3.075 age, see that? Plus 5.398 height. And we have age and height as significant predictors, and you see these beta coefficients, these standardized regression coefficients reported with the t-values and, you know, significance at alpha equals 0.05 in both cases. Okay. Exercise number 2, examine whether the key assumptions of multiple regression are met. Normality, homogeneity of variance, collinearity. Let's take a look at this. Does this meet the assumption of normality? Maybe, maybe not. The jury's out on this one. Is this a normal distribution, or does this contain a negative skew? I don't know. Typically, we like these data points sort of close to the line. So kind of normal, but kind of not. All right. Does this meet the assumption of homoscedasticity? Okay. Typically we have data points equally distributed on either side of this line. So, you know, again, another way of looking at homoscedasticity, look at the variances for the respective variables. Look at the variances for the respective, are those variances close to each other or not close to each other? This particular graph of residuals suggests not a whole lot of homoscedasticity. Here we have the assumptions. We have satisfied the collinearity diagnostics, okay, tolerance and VIF are both within acceptable limits. And just to take a look at our output here, you know, again, we have, a predictive model. So what we're saying here is that with homoscedasticity and the normality assumption, it could be affecting the accuracy of our prediction. Okay, because we have not totally satisfied those two assumptions. Okay, so it's very important that we check assumptions before we actually run the multiple regression equation. Number 3, a researcher would like to include histology in the regression analysis. It currently has 3 levels. Okay, so we see these 3 levels, and it wants us to create dummy codes. So it's actually going to reduce these categorical situations to something a bit more specific. And this specificity is going to be represented in zeros and ones. Okay, so we're going to create dummy codes, old and new values, and then check the coding using a frequency table. How many dummy variables should be created? 2 dummy codes, 1 less than dummy code than the number of levels of the variable. Typically, that is how it's done. What are the old and new values for the dummy codes? Okay. If histology 2, then histology 2 equals 1. If histology is less than or greater than 2, then histology 2 is 0. So we see 1 and 0, which is converting some categorical variable to a scale that uses coding with 1s or 0s, and it's typically yes and no. Yes, no, 1, 0, whatever. And this just tells us the frequencies. We have 24 1s and 17 no's. Okay, again, if there are any questions, please address them to me on the discussion board. Thank you so much for attending this conference this morning, and we will see you very, very soon for module number 3. Have a good day.